Hello and good morning. This is your instructor Mehak Rohra and welcome to the chapter Chemical Equations. In this chapter, we would be studying about physical and chemical changes, how do we distinguish them, some kind of examples to demonstrate physical changes and chemical changes. We will study three activities that will demonstrate what can happen during a chemical change. We will then study what chemical reactions are and what constitutes a chemical equations. We will study them by giving some sort of examples, and then we will try and write chemical equations followed by some laws. In this session, we will summarize all that I have told you right now and discuss what we're going to study in the next session. So without further ado, let's get started. If you think about chemistry, it is that branch of science that deals with the formation of new compounds from pre-existing ones. You mix two different kind of reactants and you get a different kind of product. You provide them heat, you sometimes provide them ice, you provide them a different kind of temperature, and something else happens. Breaking of old bonds and formation of new ones take place. Chemistry does involve a kind of change. That change can be temporary, that change can be permanent. But those two changes are broadly classified into two types. The change that you see is either a physical change, or the change that you come across is either a chemical change. Our concentration will be towards the chemical changes, but before that, let's discuss what a physical and a chemical change is to be able to distinguish them properly. Physical changes. By definition, physical changes are changes in which no new substance formation takes place. Hence, physical changes are reversible. It means that if you give a certain amount of opposite conditions to the prior reaction, you can get that reactant back. Reverse engineering the conditions can bring back the original substance. For example, you provide heat to melt wax. So that melted wax then, after a certain temperature that is provided to it, will cool off and still form wax. Wax will not turn into liquid honey, and liquid honey will not turn into liquid wax. It will be that the melting of wax will result after cooling on in the formation of wax only. Hence, it's a reversible change, and such a change is a physical change. One other example that we can discuss is conversion of water into vapor on heating. You know that water boils at 100 degrees Celsius and is converted to steam. But if you provide the right conditions and if you reverse engineer these conditions and keep decreasing the temperature and do the process of condensation, the water vapor can come back to water. Hence, no new substance formation takes place. Two examples that we just discussed are melting of wax and conversion of water into vapor. Both of them are examples of physical changes. Let us now study about chemical changes. Chemical change is a change or a process in which a new substance is formed. That if you provide a certain kind of conditions, a certain kind of temperature, chemical conditions, then if you want to get that substance back, you cannot. Hence, even you can not reverse engineer the conditions of the reaction to get back the original substance. For example, when water was turned into vapor, you could provide the right temperature, the right process of condensation to get that vapor that you collected and turn it back into water. Such changes are reversible, but chemical changes are irreversible. This does not take place in a chemical change. Let me give you a daily example. Formation of curd from milk. Some kind of bacteria reacts with milk and a little bit of curd to turn that whole milk into curd. A certain temperature condition is also given to this process so that it can take place properly and curd can be formed from milk. But once curd is made, this is a different substance. It cannot go back to being milk. Even if you reverse the temperature, if you reverse the bacteria, it will not go back to being milk. Milk has now, after reacting with certain chemical and bacterial substances, has formed curd. Curd is a different substance than milk. Hence, this change is actually irreversible. Since this change is irreversible, this change is considered a chemical change. One more technical example to understand a chemical change is also of the diagram that has been represented for you on the right hand side of the slide is burning of magnesium ribbon. A ribbon that is made of the element magnesium, when it burns with air in appropriate conditions, it produces that flame and leaves a residue. But if you try and reverse engineer the conditions, you cannot get the magnesium ribbon back from that residue that is left. This is an example also of a chemical change which is irreversible. You cannot reverse engineer the conditions to get the original substance back. No matter what you try, you cannot get the magnesium ribbon in the same structure possible from the residue that is now a new substance. These are physical and chemical changes. Chemical changes are changes in which new substances are formed and due to some kind of conditions. Physical changes are changes that lead to new substance formation, since changes that are physical are irreversible. Now let us study some more examples of chemical changes. The process of digestion. Whenever you digest food and it travels down your food pipe, it gets mixed with the hydrochloric acid that is present in your stomach. It turns into smaller food, and when it is forced out of your body, that is a new waste substance. This process of digestion is irreversible. It's a chemical change. Burning of crackers. The material that constitute crackers after being exposed to some kind of heat, light or fire goes and burns into ashes after producing a colorful show. You cannot reverse engineer this particular reaction also, right? You cannot provide condensation processes, you cannot reduce temperature and make those ashes of the crackers come back to being crackers. They cannot. A new substance is formed. That substance was ash and residue and other carbon compounds, and we cannot get them back to their original state. Hence, the process of burning of crackers is an irreversible chemical change. Next, the process of respiration. You breathe out CO2 when you take in O2. A lot of other processes that are involved in making these compounds take place. What you take in are reactants other than oxygen. They go through some chemical changes in your body and they lead out to give you some energy that is used for your body, and you liberate out CO2 as a residue. All these compounds that I mentioned that are formed are all products, and they are different compounds. They are new compounds. They are new substances. And next, adding powdered lime to water. Adding quicklime to water or adding powdered lime to water is also an example of a chemical change. If you mix this, it leads to a formation of a new substance. One of the activities related to this example will be done in the later session. Ripening of mango is also a chemical change. Once a mango is ripe, you cannot go back to making that mango being raw again. The process of heating, oxidation and other chemical processes that take place on the mango and whatever temperature conditions that are given, even if they are reverse engineered, you cannot go back to having that raw mango in your hand again. So ripening of mango is another example of a chemical process or a chemical change. One of a more technical example is exposing iron nails to the moisture in air for a longer period of time. If you see, when exposed to moisture, if an iron nail is kept in air for a long time, it gets rusted, or you see a brown coat is deposited over it. That new substance once formed cannot exactly make that iron go back to its original position if you remove the moisture, if you remove the air. That is not going to happen. Corrosion will take place. The process of formation of that brown layer over iron nails, if they are kept in air for long and exposed to moisture, one of those processes is called corrosion, and corrosion in general cases is irreversible. This is one of the technical examples of a chemical change. Let us now discuss the activities that will help you understand what all can happen during a chemical change. The first activity, we take quicklime. Quicklime's formula is calcium oxide, and we add quicklime to 10 ml of water. And if we observe that beaker, then you will see that the beaker that you have in which you added these two contents, it will feel hot, and when you mix this solution, a colorless solution is formed. If you add red litmus paper to this solution, then this solution will become blue. This will indicate that the solution that was just formed when you mixed quicklime with water was a basic solution. I have written and I have presented the reaction that takes place. You don't have to worry about how this came to be because we will study about it. But just to give you the reaction that takes place, it's calcium oxide, CaO, plus water, that is H2O. It leads to formation of calcium hydroxide when you mix quicklime with water. The temperature of the beaker rises because it releases a lot of heat. Just a quick tip, that bases become blue. If you remember this line, then you can always remember that red litmus paper, if you dip in solutions that are basic, they will become blue. B for bases and B for blue. Bases become blue. Let us now go to the next activity that will demonstrate a different kind of chemical change. A different kind of thing that will happen when a chemical change is taking place. We take about 100 ml of water in a beaker and we dissolve a small quantity of sodium sulfate. Sodium sulfate is a white solid and it's a chemical compound. It is made of two compounds, sodium and sulfate. Sulfate is made of sulfur and oxygen. You don't have to worry about this particular example also and the formula. You just have to observe what kind of changes are taking place. We take another 100 ml of water in another beaker and we dissolve a small quantity of barium chloride. The barium chloride has a formula of BaCl2. When we mix both of them in water in different beakers, definitely, you will see that the solution or aqueous solution, if any compound is mixed in water, it is referred to as aqueous solution of that compound. So this aqueous solution of sodium sulfate is colorless. That is an observation. Solution of barium chloride is also colorless. So when you see there are these two white solids, when you mix them in water, they dissolve in water and both of these solutions, they turn colorless. Now, if you mix both of these solutions, you will observe that after some time, a white residue is found at the next beaker in which both these solutions are mixed. If you look at the diagram that has been presented to you on the right hand side, you will see that on one hand we have sodium sulfate solution, on one hand we have barium chloride solution. If you mix them and if you pour them in a beaker, barium sulfate will be formed and barium sulfate will leave a white residue or a white precipitation. So you see, when you mix these two solutions, a different precipitate was formed. The particular reaction that is involved will be given to you in the coming sessions when we discuss chemical equations. But it is barium chloride that reacts with sodium sulfate, which leads to the formation of sodium chloride and barium sulfate. Barium sulfate is what leaves the white precipitation. Let's go to the third activity. We take zinc granules. Granules are very small pieces of the metal zinc in a conical flask. Conical flask is similar in structure to the flask that has been given to you on the right hand side of the diagram, of the slide, If we add 5 ml or less of dilute hydrochloric acid that is mixed in water is dilute hydrochloric acid, to zinc granules in a conical flask, and if we observe the changes, we will see that when dilute hydrochloric acid mixes with zinc, then hydrogen gas, H2 gas, is released. How to confirm that H2 gas is released is that when we light up a matchstick and we bring near the opener or the mouth of that particular conical flask, that flame will go off because hydrogen cuts off oxygen supply for it, and hence the flame will go out. This will confirm for you that hydrogen gas is evolved. So the bottom of the glass, when bottom of the flask, when touched, you will see that it is hot. Hence some kind of rise in temperature also took place when both of these were mixed together. The reaction that is involved I have given to you in the slides. Zn, that is the element representation of zinc, plus HCl, that is hydrochloric acid, leads to the formation of zinc chloride, and hydrogen gas is evolved. Now that we studied all three activities, we actually observe what happened during a chemical reaction. Most of the original substances, they lost their characteristic properties, and then the products with different physical states and different colors and different states, they were formed. Since you saw in two of these activities there was a rise in temperature, hence chemical reactions or chemical changes, they may be exothermic or endothermic. Exothermic reactions are reactions in which heat is liberated or heat is given out in the chemical reaction as a product. Endothermic reactions are reactions in which heat is used as a reactant. Heat is absorbed by the products that are by the objects or by the chemicals that are being mixed together. Sometimes in chemical reactions you see that an insoluble substance or a precipitate or a residue is formed. When you saw that we mixed sodium sulfate with barium chloride, a precipitate of barium sulfate was formed. In the third example, we saw that hydrogen gas was liberated. So we can conclude that during a particular chemical reaction, gas evolution is possible. Insoluble substance formation is possible. And when a chemical reaction takes place, there may be a change in state. It means a substance can go from being a solid to being a liquid or being a semi-solid or being a gas in an irreversible process, though, if given the same conditions. Hence, what happens during a chemical reaction? We lose characteristic properties of the chemicals that were mixed together or the substances that were mixed together. The reaction that takes place can release heat, or the reaction that took place might need heat. Then an insoluble substance, when you mix two different solutions, it may be formed, it may not be formed. A gas may be evolved, it may not be evolved. There might be a change in state of that substance, or there might be no change in state. It depends on the factors that influence that chemical reaction. You will study about them later. Let's go to what a chemical reaction is and what a chemical equation is. Any process in which a substance goes under a chemical change is called a chemical reaction. Now, when we write about chemical reactions, they might be long and sometimes not precise enough. Then reactions are therefore they are expressed in the form of equations. Why? Because equations have symbols and directions that make it easier to understand. The two substances that are mixed or that go through that chemical reaction, they are called reactants, and they appear on the left hand side of a chemical equation, while the substance or the new substance that is formed after the chemical process reaction is called product, and they appear on the right hand side of the reaction. Reactants and products mostly are separated by an arrow. As you see in the examples that I have provided to you, magnesium and oxygen are two reactants. They are presented on the left hand side, and when they react under certain conditions, magnesium oxide or a new compound called MgO is formed. If you see this example, that was reaction of quicklime with water, CaO and H2O being reactants present on the left hand side react together or are mixed together under certain conditions, and they form calcium hydroxide. Third example, zinc when acting with hydrochloric acid, dilute hydrochloric acid, leads to the formation of ZnCl2, which is zinc chloride, and leads to the liberation of hydrogen gas. Zn and HCl being two reactants on the left hand side, and ZnCl2 and H2 being the products that are formed, being on the right hand side. So, the substances which undergo a chemical change in the reaction are called reactants. For example, magnesium and oxygen. And the new substance that is formed after the chemical change takes place is called product or products, like magnesium oxide. When magnesium and oxygen react under certain conditions, a new product that is formed after the chemical reaction is magnesium oxide. The arrowhead or the arrow actually shows the direction in which the reaction proceeds. So, when magnesium and oxygen react together, it goes towards the direction of magnesium oxide. Arrowheads show direction. If there is one or more reactant or product that is involved in the reaction, we indicate them by using a plus sign between them. So, if magnesium and oxygen are reacting with each other, we say Mg plus O2 to form 2MgO. That is the entire chemical equation. To give a professional definition to chemical equations, I will say that the symbolic representation of a chemical reaction using chemical formulae of the compounds and symbols of elements that all are involved in that reaction is called a chemical equation. For example, if I say zinc reacts with sulfuric acid to form zinc sulfate and a gas is evolved, we can write this equation in two manners. One, we can express it in the form of words. For example, zinc plus sulfuric acid, arrowhead leads to the formation of zinc sulfate plus hydrogen. But this would be a bit difficult to understand. Hence, we use symbolic representations. The symbol of zinc is Zn. The formula for hydrogen sulfuric acid is H2SO4. The arrowhead determines the reaction or the direction in which the reaction is proceeding. The reaction is proceeding towards the formation of zinc sulfate, represented by ZnSO4 as given in the slide, plus H2. Now, zinc, Zn and hydrogen sulfide or sulfuric acid actually are the reactants, and the formation of zinc sulfate and hydrogen, that is the products. The first one is called word equation of a chemical reaction. The second form, the symbolic representation, is a chemical equation the symbolic representation of a chemical reaction that takes place under certain conditions. If I were to give you one more example, look at the animation that is being played in front of you. Two molecules of hydrogen and a molecule of oxygen, O2, they react with each other. The arrowhead represents the direction in which the reaction is proceeding, and they combine together to form 2H2O, which is also the symbol of water. Water is made up of hydrogen and oxygen. Now, chemical equations that are written by us to represent chemical reactions, they have to obey a law. All chemical equations that are written down must obey the law of conservation of mass. The law of conservation of mass states that the total mass of products is equal to the total mass of the reactants. Any equation, precisely any chemical equation that is written down, must always be balanced. Hence, the total number of atoms on the left hand side for each element must be equal to the total number of atoms on the other side of each element. If I were to give you an example, look at the reaction look at the reaction of zinc plus sulfuric acid that leads to the formation of zinc sulfate plus hydrogen gas being evolved. We have written the chemical equation that represents this chemical reaction. If you see, one element of zinc is on the right hand side and one atom of zinc is on the left hand side. Two atoms of hydrogen are on the left hand side and two atoms are on the right hand side. Similarly, one sulfate molecule is on the left hand side and one sulfate molecule is on the right hand side. Hence, there is no imbalance. As many elements we used, as many substances we used to make all the reactants and to make the reactants react with each other, after the particular reaction we got the same amount of elements in different orders, but the same amount of elements. Hence, if you add the total masses of all elements on the left hand side, it will be equal to the amount of the total mass of all elements on the right hand side. So the equation that I just gave to you, where zinc reacts with sulfuric acid to form zinc sulfate and gas hydrogen, is actually a balanced chemical equation. All chemical equations written down obey law of conservation of mass. Balanced versus imbalanced equations. An equation in which the number of atoms of each element is same on the reactant side and on the product side, as we just saw, is called a balanced chemical equation. Whereas an equation in which number of atoms is not the same on the reactant and the product side is called an imbalanced chemical equation. Let us see the example of an imbalanced and a balanced chemical equation. When zinc reacts with hydrogen sulfate or sulfuric acid, we see zinc sulfate is formed with hydrogen gas being evolved. If you see, the number of atoms of each element on the right hand side is equal to all the number of atoms of each element on the left hand side. Therefore, this equation is balanced. Let's try and observe the imbalance equation now. You see that zinc is balanced, sulfate molecules are balanced, but when it comes to hydrogen, there are two molecules of hydrogen gas, which is H2, but there is only one on the left hand side, while there are two on the right hand side. Such an equation does not obey law of conservation of mass. Since it does not obey law of conservation of mass, this is an imbalanced chemical equation which isn't right. It is very important to balance chemical equations. That is it for this session. Let us now discuss what we studied in this particular session. What are physical changes? Physical changes are changes in which no new substance is formed after a particular reaction. Such changes are reversible changes. You can get back the original substance if you reverse engineer the conditions. Chemical changes. Chemical changes are changes in which new substances are formed, maybe from pre-existing ones. Chemical changes are irreversible changes. For example, burning of magnesium ribbon. Chemical changes sometimes are or may be endothermic or exothermic. Endothermic means these reactions absorb heat. Exothermic means these reactions or changes might liberate heat or give out heat. Chemical changes might cause a change in state of a substance or of an element. Chemical changes may require the particular reaction to cause a change in color or to cause a change in other characteristics such as shape, size, structure. Sometimes chemical changes may require or may lead to a formation of a precipitate like a residue. For example, when we mixed sodium sulfate with the barium chloride solution, we got a precipitate of barium sulfate, which was white in color. The symbolic representation of a chemical equation using chemical formulae of compounds and symbols of elements that are involved in the reaction is called a chemical equations. Elements that undergo these reaction are called reactants, and they are represented on the left hand side of the chemical equation, and those elements that are formed during or after this chemical reaction is called or are called products. They come on the right hand side of the chemical equations. Chemical equations obey law of conservation of mass, that is, number of atoms of each element must be same on the right hand side and on the left hand side. Chemical equations need to be balanced. That is all for this session. In the next session or in the coming session, we will be defining balanced chemical equations in a more formal manner. We will identify steps that will help us write a balanced chemical equation, or that will help us write an initial equation and help us balance it afterwards. We will try and give ourselves a lot of different examples, and we will try balancing all these different chemical equations through the steps that we studied. Then we will try and interpret all these balanced chemical equations, and then we will make a summary of what we study in that session. After we are done with this, we will try and recall the whole chapter of chemical equations. That is all for now. I hope you all are safe. Till then, thank you and be safe.